Rotational inertia of a solid object. So now we're going to have to use some calculus. First thing we do, I draw a picture. I've got my thin rod, its uniform density, and it's located on the x-axis between x equals 0 and x equals L, the length of the rod. Alright, so I'm going to pick, here's our equation we're using. The rotational inertia is the integral of r squared dm. So I have to pick some little chunk, some little piece out here, dm, some arbitrary location. Don't pick a special place, just pick some arbitrary location. Call that little chunk dm. And r is the distance from the axis of rotation to dm. And dm, we've talked about in an earlier video, that's our density multiplied by the length. In this case it's a one-dimensional object, so our length here of that is dx. So rho dx. And because it's uniform density, I can call that the mass over the length times dx. Okay, and what is r? R is the distance from the axis of rotation to dm, so that would be this distance here. Would be r. And what is that in our coordinate system here? That's just x, right? Alright, or x. So our integral in our coordinate system here becomes r, I'm going to replace with x, so it's the integral of x squared, and dm I'm going to replace with m over L dx. And we integrate over the object, and our object goes from x equals 0 to x equals L. So we've got m over L, because we have to add up the contribution of every little chunk of the object, and it goes as r squared times the mass of that little chunk, and we're adding them all up. So what do I get here? I get m over L, x cubed over 3 from 0 to L, and I get m over L, L cubed over 3 minus 0, 1/3 m L squared. So 1/3 the mass of the rod times the length of the rod squared. That's the rotational inertia of the rod rotating about an axis perpendicular to the rod and through its endpoint. So I've added another drawing here. Let's take a look at what happens when we go through the center point of the rod instead of the end point. So in the previous example, I never wrote it on here, but this rod was rotating about the y-axis like that. And now it's also rotating about the y-axis, but the axis goes through the center of the rod. So would you expect the moment of inertia to be less in the second case, or more, or the same? I would expect it to be less, because in the first example, some of the rod, some of the mass out here is very far away. It's L away from the axis of rotation, and it goes as the square of that distance, so it has a big contribution. Some is very close in, but some is very far away. Whereas in this case, there's nothing, no mass that's more than L over 2 away from the axis of rotation. It's much closer to the axis of rotation. So this will be much easier to get the rod spinning in this orientation, and it's much easier to get it to stop spinning if it already is spinning than it would be if the rod was rotating about its end point. So let's see if we get an answer that's smaller. So I, the rotational inertia, or the moment of inertia, the rotational inertia is going to be the integral of, again, it's the distance. We're going to pick some arbitrary dm, and the distance to that point is x, and that is dx, so it's going to be x squared m over L dx, just as it was in the last example. And we're integrating over the entire rod, so minus L over 2 to plus L over 2. M over L, x cubed over 3 from minus L over 2 to plus L over 2. So there's two of these now. And what do I get? I get 1/12 ml squared, which is less than 1/3 ml squared. So the moment of inertia, the rotational inertia, those two terms are interchangeable, moment of inertia and rotational inertia, is much less in this case because the mass is located closer in to the axis of rotation. Okay, and I've drawn the third situation here where the rod is located on the x-axis between x equals a and x equals a plus L. It's rotating about the y-axis, which means that it's going to make basically a washer shape, right? A disc with a hole in the middle of it as it rotates around the y-axis. And let's take a look at our formula. The integral, again, it's going to be x squared because here's our small chunk dm, and it's located a distance x from the axis of rotation. And our dm is m over L dx because it's uniform density, and we're integrating from a to a plus L. So I'm just going to skip to the chase here. I got 1/3 ml squared plus a ml plus a squared m. And I'm just going to leave it like that. And we're going to check these answers again using another technique in the next video to see if we get the same thing.